Welcome to The Explainer. Today, we're going to go on a quest to figure out how computer scientists solve the unsolvable. We're talking about challenges that are so massive, so complex, they can seem completely impossible. So let's just dive in. All right, so let's start with the big one, right? The question that really drives so much innovation. When you are staring down a problem that feels genuinely impossible, where do you even start? For a computer scientist, the answer always starts with a plan. It's called an algorithm, which is really just a fancy word for a precise step-by-step recipe. Every single step has to be crystal clear. You need a defined start, and you need a defined finish. Okay, to make this feel real, let's use a classic puzzle. It's called the knapsack problem. Just imagine you're a treasure hunter. You've got this knapsack and it can only hold so much weight. In front of you is a room just full of treasure and every item has its own weight and its own value. Your mission? Pack your bag with the absolute most valuable loot you can without the whole thing bursting at the seams. Now, the first thing you'd probably think of, the most obvious way to solve this, might seem simple. But as we're about to see, when problems get really big, this simple way is often a truly terrible idea. Yeah, that obvious approach, we call it brute force. You just try every single possible combination. You try just the diamond, check the value, then just the key, check the value, then the diamond and the key together. And you just keep going, listing out every single possibility until you've checked them all, and then you can finally pick the best one. And you know what? For a really small number of items, maybe 5, this strategy is totally fine. It's manageable. You could probably sit down with a pen and paper and figure it out in a few minutes. No problem. But this is where things go completely off the rails, and they go off fast. Just look at this chart. With 5 items, we're talking 32, maybe 120 combinations. Fine. But jump to just 20 items. The number of possibilities just explodes. It goes from over 1 million in one case to, well, in a factorial problem, it's 2.4 quintillion. That's a 2 with 18 zeros after it. A computer trying to check every single one of those would literally take longer than the age of the universe. That's what we mean by an impossible problem. Okay, so yeah, brute force is out. It's a non-starter. We need smarter strategies. But to know if a strategy is actually smart, we need a way to compare them. We need some kind of scoreboard for efficiency. And this leads us to a really crucial question. How do we create a standard speed rating for our algorithms? I mean, you can't just time it on your watch, right? Your super fast gaming PC is going to get a totally different time than my 10-year-old laptop. We need a universal way to talk about this. And the solution is this thing called Big O notation. The easiest way to think about it is as a promise for the worst-case scenario. It answers the question, as the problem gets bigger, how much slower is this algorithm going to get? Big O gives us the ceiling. It guarantees the performance will never be worse than this. And on the flip side, you've got omega notation. This is the best-case scenario. If Big O is the ceiling, omega is the floor. It guarantees that no matter how lucky you get, the algorithm will never be faster than this. It's our performance baseline. Okay, so armed with our new scoreboard, let's check out our first smart strategy. It's this tempting little shortcut that sometimes is just incredibly effective. It's called a greedy algorithm, and honestly, it's beautifully simple. At every single decision point, it just picks the option that looks best right now, in this very moment, without ever worrying about what might happen down the road. This whole take the best stuff first approach is actually perfect for certain kinds of problems. Let's go back to our knapsack. If we could take fractions of items, like instead of whole gold bars, we could scoop up gold dust, then always grabbing the most valuable dust per pound would give us the perfect solution every time. It works because each choice doesn't mess up our future choices. But what if the best choice now isn't the best choice overall? What if grabbing that one huge diamond fills up your knapsack, leaving no room for 3 slightly smaller gems that, together, are way more valuable? When a short-sighted choice can lead to a really bad outcome, well, that's when you need a totally different strategy. This strategy is called divide and conquer, and it is as straightforward as it sounds. First, you divide the big problem into smaller, identical pieces. Second, you conquer each of those little pieces by itself. And third, you combine all those little solutions back together to solve the original big problem. And this diagram shows you exactly how it works. You see that big problem at the top? It gets split. Then those pieces get split again and again, creating this kind of tree. You just keep dividing until the problems at the very bottom are so simple they're trivial to solve. Then you just work your way back up, combining the answers as you go. Now, our third strategy is pretty similar to divide and conquer, but it's got this really clever twist. What if, while our algorithm was solving all those tiny subproblems, it could actually remember the answers that it already found? This is the huge idea behind dynamic programming. It also breaks problems down, but it's built for one specific situation, when those smaller pieces overlap. I mean, think about it. Why would you solve the exact same puzzle twice? You wouldn't. Instead, dynamic programming solves each unique little problem just one time and saves the answer in a table so it can be looked up instantly later on. So, this slide really gets to the heart of the difference. On the one hand, divide and conquer is for problems that break down into totally separate, independent pieces. But on the other hand, dynamic programming is the hero for when those pieces are all interconnected, and you'd end up solving the same subproblem over and over again. It is all about being efficient by having a good memory. So we've got these really powerful tools in our arsenal, right? We've got greedy shortcuts, we have divide and conquer, we have programming with memory. But even with all of that, we still run into a class of problems that are living right on the very edge of what is even computationally possible. And maybe the most famous of all of these is the traveling salesperson problem. The idea sounds so simple. You have a list of cities, and you have to find the absolute shortest route that visits each city just one time and then returns home. But solving this simple-sounding puzzle has massive implications from everything from delivering packages to designing circuit boards. Finding the one perfect, absolute best solution for the TSP is what we call NP-hard. Now, in simple terms, that just means that while it's really easy to check if a route somebody gives you is short, we don't know of any way to actually find the shortest route that's much faster than that original brute force method. As you add more cities, the problem just explodes again, and even our smartest strategies can't promise a perfect solution without taking an impossible amount of time. But here's the real takeaway from this explainer. Greedy choices, divide and conquer, dynamic programming, these are not just abstract ideas for computers. They are powerful mental models. They are structured ways of thinking that you can apply to any complex challenge you face. So the question isn't just for a machine, it's for you. What impossible problem will you solve first?